Hello and welcome. In this video, we'll explore a fascinating and beautiful result from classical geometry. By the end of this lesson, you will be able to prove that the three circumcircles of specific triangles formed by the medians of another triangle all intersect at a single point. Let's state this more formally. Suppose we have a triangle ABC. The medians AD, BE, and CF intersect at a point G, which we call the centroid. Now, we can form three smaller triangles. The first is triangle AEF. Which connects the vertex A to the midpoints of the opposite two sides. The second is triangle BFD. Using vertex B and the other two midpoints. And the third is triangle CDE. Connecting vertex C to its adjacent midpoints. What we're going to prove is that these three circles, despite being formed from different parts of the main triangle, somehow pass through a single common point. It's a surprising and elegant result. Our strategy to prove this will be to take two of the circumcircles, find their intersection point, and then prove that this third circumcircle also passes through it. Let's begin by considering the circumcircles of triangles BFD and CDE. We can visualize their intersection. They both pass through point D. D is the midpoint of BC, and it's a vertex for both triangles. So, D is one intersection point, but two circles typically intersect at 2 points. Let's call the other intersection point P. Our goal is to find this point P and show all three circles pass through it. We'll use a technique called power of a point. The power of a point theorem tells us that if we draw any secant line through a point P, the product of the lengths from P to the two intersection points with a circle is constant. Let's apply this to our setup. Consider point P relative to the circumcircle of AEF. If P is on this circle, its power must be 0. Let's draw a line through P that intersects the circle at A and E. The power of P, with respect to the circle, is the product of the directed distances PA and PE. Since P is outside the circle in the diagram, this product, Pennsylvania times PE, must be positive. The challenge is that this depends on the specific choice of the line. There's another, more general way to define the power of a point, which is independent of the line. A more powerful, and ultimately more useful definition for us, is that the power of a point P with respect to a circle is equal to the square of its distance from the center minus the square of the radius. This value, d squared minus r squared, is the same for any secant line or tangent line we draw from P. We can use this to our advantage. Okay, let's use the power of a point theorem. First, we need coordinates for our points. A general coordinate geometry approach can get very messy. A more elegant method is to use a special type of coordinate geometry called complex numbers. Let's assign complex numbers, represented by lowercase letters, to the vertices of our triangle. Let vertex A be represented by A, B by B, and C by C. So, we have the complex numbers A, B, and C. Next, let's find the complex numbers for the midpoints of the sides. Since D is the midpoint of BC, its complex number is simply the average of B and C, so D equals B plus C over 2. Similarly, E is the midpoint of AC, so E equals A plus C over 2. And F is the midpoint of AB, so F equals A plus B over 2. Now, we can use a known formula for the power of a point P, represented by complex number P, with respect to the circumcircle of any 3 points, say x, y, z. This formula states that the power of point P with respect to the circumcircle of x, y, z is equal to P times its conjugate, minus the complex number for the center of the circle, let's call it W, times the conjugate of P, minus the conjugate of W times P, plus the square of the radius, r squared. The beauty of complex numbers is that we can handle the power of a point purely algebraically without needing geometric arguments. Our goal is to show that there is a point P that makes this power 0 for all three circumcircles. To make our calculations manageable, let's use a clever trick. We can place the circumcenter of the triangle AEF at the origin. This might seem arbitrary, but any two geometric figures can be transformed without changing their fundamental properties. By moving the AEF circumcenter to the origin, we simplify the formula for its power. If the center of the circumcircle for triangle AEF is at the origin, the center W becomes 0. This simplifies our power of a point formula dramatically. For the AEF circumcircle, the power of a point P is just P times its conjugate minus r squared. The simplified power of a point formula for the AEF circle is P times its conjugate minus r squared. Now, if our point P lies on this circle, its power must be 0. So, if P is an intersection point, then P times its conjugate must equal r squared. This is a key simplification. A well-known property of triangles is that the circumcircle of AEF has a center that is the midpoint of the circumcenter of ABC and the centroid G. This property allows us to relate the geometry of the smaller triangle to the main triangle. The circumcenter of ABC is the point where the perpendicular bisectors of the sides meet. So, the complex number for the circumcenter of ABC, which we'll call omega circumcircle, is just 2 times the center of our AEF circle, since the AEF center is the midpoint. Now, remember that the circumcenter is equidistant from the vertices, so the distance from the circumcenter of AEF to A, E, and F is the same. Let's call this radius R10AF. This means the distance from the AEF circumcenter at the origin to A, E, and F is all equal to r squared. This gives us the equation that A times its conjugate, E times its conjugate, and F times its conjugate are all equal to r squared. We're almost there. We have the circumcircle of AEF with its center at the origin and power given by P times its conjugate minus r squared. Now, let's find the power of a point P with respect to the circumcircle of CDE. The circumcircle of CDE has its own center. Let's call it W_CDE and its own radius. The power of a point P relative to this circle is given by the general formula we saw earlier. So the power of P is P times its conjugate minus WWCDE times the conjugate of P minus the conjugate of WWCDE times P plus the square of the radius. This formula still looks complicated. Let's simplify it using the same trick we used for the AEF circle. Let's place the circumcenter of the CDE triangle at the origin. Then, W_CDE is 0, and the power simplifies to P times its conjugate minus R prime CDE squared. This means for a point P on the CDE circle, P times its conjugate must equal R plus CDE squared. But now we have 2 different points for the origin. This is a problem. The power of a point must be defined relative to a fixed coordinate system. We can't change the origin for each circle. This is a very common misconception and an important learning point in geometry. The power of a point is dependent on the position of that point and the circle, which are defined in a coordinate system. We cannot simplify by placing the center at the origin for both circles simultaneously, unless the circles are identical. Therefore, we must go back to our original approach. Place the center of the AEF circumcircle at the origin and keep it there. Then, we must use the general power formula for the other 2 circles. Let's restart the calculation for the CDE power with the origin at the AEF circumcenter. This is a more robust and correct way to proceed. Okay, let's try a different strategy that avoids the complex number power of a point formula and focuses on the geometric properties of these circles. The strategy will be to prove that the 3 circumcircles share a common radical axis. The radical axis of 2 circles is the locus of points from which the tangent lengths to the 2 circles are equal. It's a straight line, and if the circles intersect, their radical axis is the line connecting their intersection points. A crucial theorem about radical axes is that the radical axes of 3 circles, taken in pairs, are concurrent. This means they all meet at a single point, called the radical center. So, we need to prove that the circumcircles of AEF, BFD, and CDE have a common radical center. We can see from our diagram that the circumcircles of BFD and CDE intersect at D. Therefore, the radical axis of the BFD and CDE circles is the line connecting their intersection points. If they only intersect at D, their radical axis is the common tangent at D. So, their radical axis is the tangent line to both circles at D. This line is perpendicular to the line connecting the centers of the 2 circles. This approach is more concrete and visual and allows us to use more familiar geometric properties. Let's summarize. We will focus on 2 circumcircles, the circumcircle of AEF and the circumcircle of CDE. We will find their intersection point and then show that this point must also lie on the 3rd circumcircle, that of BFD. This will involve using the property of the radical center To make the problem manageable, let's look at a well-known related geometric figure called the pedal triangle. This will give us a key insight. The pedal triangle is formed by the feet of the altitudes from a point P to the sides of a triangle. The crucial property here is that if a point P lies on the circumcircle of a triangle, its pedal triangle is a straight line, not a triangle. This line is known as Simpson line or Simpson's line. Now let's connect this to our problem. We are looking for a common point P for the three circumcircles. Consider our three circumcircles. A remarkable theorem by Euler proves that our circumcircles are actually the pedal circles of a specific point relative to the medial triangle. So this means that we are looking for a point that lies on the circumcircle of all three of our triangles. This special point is the circumcenter of the main triangle ABC. So the point P we are looking for is the circumcenter of the main triangle ABC. Let's call it O. We need to prove that the circumcenter O of triangle ABC lies on the circumcircles of AEF, BFD, and CDE. By using this result, the problem has shifted. Instead of finding the intersection of three circles, we must prove that the circumcenter of the main triangle has a specific property. We will now prove our conjecture. We need to show that the circumcenter O of triangle ABC lies on the circumcircle of triangle AEF. The proof for BFD and CDE will follow a very similar logic due to the symmetry of the figure, so proving it for one triangle is sufficient. Remember, AEF is a triangle formed by vertex A and the midpoints E and F, and O is the circumcenter of the main triangle ABC. This means the distance from O to A, B, and C is the same, equal to the radius r of the circumcircle of ABC. Our goal is to prove that O, A, E, and F are concyclic, meaning they all lie on the same circle. We can do this by showing that the quadrilateral AEOF is cyclic. A quadrilateral is cyclic if and only if the sum of its opposite angles is 180 degrees. Since E and F are midpoints, the segment EF is parallel to BC. This means the smaller triangle AEF is similar to ABC. Therefore, angle AEF is equal to angle C. Now, let's consider angle EOF. The central angle EOF subtends the arc EF in the circumcircle of AEF. The inscribed angle EAF, which is angle A of the main triangle, subtends the same arc. Since the central angle is twice the inscribed angle, we have that angle EOF is equal to 2 times angle A. We also know that the angle subtended by the side BC, at the center O, is 2 times angle A. This means angle BOC equals 2 times angle A. So angle EOF equals angle BOC. So, since angle EOF equals angle A of triangle AEF, and angle BOC also equals 2A, we are led to a contradiction if we try to prove AEOF is cyclic this way. This shows a small but significant error in our approach. The circumcircle of AEF is not the same circle that passes through O, E, and F. It turns out the circumstances of AEF, BFD, and CDE are all congruent to one another. Each of these circles is congruent to the circumcircle of the medial triangle. In fact, a beautiful theorem known as the 9-point circle theorem combines these three circles and the circumcircle of the medial triangle into one. The 9-point circle theorem states that the circumcircle of the medial triangle, which is the triangle DEF, is the same circle that passes through the feet of the altitudes and the midpoints of the segments connecting the vertices to the orthocenter. Let's be clear, our three circles, AEF, BFD, and CDE, are not the 9-point circle. However, a key property of the 9-point circle is its center, which is the midpoint of the orthocenter, H, and the circumcenter O of the main triangle ABC. So the center of the DEF circumcircle is the midpoint of OH. It is the same circle that passes through the 9 special points. The intersection point P we are looking for is called the radical center of our three circles. It is a known result in geometry that this radical center is the circumcenter O of the main triangle ABC. We need to prove that these three circles intersect at O. So our task is reduced to showing that the circumcenter O of triangle ABC lies on the circumcircle of triangle AEF. This was the step that we had trouble with before, but now we have a solid goal to prove. Let's restart the proof for our claim that the common point is O, the circumcenter of triangle ABC. We must prove that the circumcenter O of triangle ABC lies on the circumcircle of AEF. That is, we must show that the 4 points A, E, F, and O are concyclic. A useful theorem states that 4 points are concyclic if the product of the segments on one diagonal equals the product of the segments on the other diagonal. However, a simpler condition is to show that a quadrilateral is cyclic. A quadrilateral is cyclic if the sum of opposite angles is 180 degrees. So, we need to show that angle A plus angle EOF equals 180 degrees, or that angle OFA plus angle OEA equals 180 degrees. The second approach is easier. Let's focus on angle OFA. Since O is the circumcenter of ABC, the segment OF is the perpendicular bisector of the side AB. Because F is the midpoint of AB and OF connects to the circumcenter, OF must be perpendicular to AB. This means angle OFA is a right angle, or 90 degrees. By the same reasoning, since E is the midpoint of AC, the segment OE is the perpendicular bisector of AC. Therefore, OE is perpendicular to AC. Similarly, angle OEA is also a right angle, or 90 degrees. Now let's find the sum of these two opposite angles in the quadrilateral AEOF. The sum of angle OFA and angle OEA is 90 degrees plus 90 degrees, which equals 180 degrees. Since the sum of opposite angles in the quadrilateral AEOF is 180 degrees, the quadrilateral is cyclic. This means that the 4 points A, E, F, and O all lie on the same circle. This is exactly what we wanted to prove. The circumcenter O of triangle ABC lies on the circumcircle of triangle AEF. So, we've shown that the circumcenter O of triangle ABC lies on the circumcircle of AEF. What about the other two circumcircles? The beauty of this proof is its symmetry. We can use the exact same logic for the other two cases. Consider the circumcircle of triangle BFD. We want to show that O lies on this circle. We would look at the quadrilateral OFBD. F is the midpoint of AB, so OF is perpendicular to AB, meaning angle OFB is 90 degrees. D is the midpoint of BC, so OD is perpendicular to BC, meaning angle ODB is 90 degrees. The sum of opposite angles OFB and ODB is 90 plus 90, which is 180 degrees. Therefore, quadrilateral OFBD is cyclic, and O lies on the circumcircle of BFD. And for the circumcircle of triangle CDE, we would look at quadrilateral ODCE. D is the midpoint of BC, so OD is perpendicular to BC. Angle ODC is 90 degrees. E is the midpoint of AC, so OE is perpendicular to AC. Angle OEC is 90 degrees. The sum of angles ODC and OEEC is 180 degrees, so ODCE is cyclic, and O lies on the circumcircle of CDE. Let's bring this all together to form our final conclusion. We began with the statement we needed to prove. Let medians AD, BE, CF intersect at G. The circumcircles of triangles AEF, BFD, and CDE pass through a common point. We established that the common point we're looking for is the radical center of the three circles. In our proof, we've shown that the circumcenter O of the original triangle ABC lies on all three of these circumcircles. This means that the circumcenter O is indeed the common point of intersection for all three circles. Therefore, the theorem is proven. The circumcircles of AEF, BFD, and CDE do pass through a common point, and that point is the circumcenter of the main triangle ABC. We have successfully proven that all three circles intersect at a single point, which is the circumcenter of the triangle. This is a wonderful example of how the simple properties of perpendicular bisectors and cyclic quadrilaterals can lead to a beautiful and non-trivial geometric result. Thank you for joining me on this proof. Let's start by drawing our triangle ABC. Next, we'll mark the midpoints of each side, D, E, and F. Now, let's draw the medians AD, BE, and CF. These medians intersect at a common point G, which is the centroid of the triangle. The problem asks us to prove that the circumcircles of triangles AEF, BFD, and CDE pass through a common point. Let's focus on triangle AEF first. Since E and F are midpoints, EF is parallel to BC and half its length. This means triangle AEF is similar to triangle ABC. Let's draw the circumcircle of triangle AEF. Now consider triangle BFD. Similarly, triangle BFD is similar to triangle ABC. Let's draw its circumcircle. Finally, let's look at triangle CDE. And triangle CDE is also similar to triangle ABC. Let's draw its circumcircle. Notice that all three circumstances pass through the centroid G. This is a known property of the centroid and midpoints of a triangle.